Presented by Caltech.
At Caltech, as you've heard, we don't shy away from big ideas and the pursuit of big science. In fact, we embrace them. So I'd like to talk to you today about the kinds of things that we do in the Division of Physics, Math, and Astronomy, which I'm a physics faculty member, where we have a rich history of building complex tools that provide ever-increasing resolution with which we can observe the wonders of nature. Today, I'd like to talk to you about new instrumentation, in fact, building an entirely new kind of observatory, one, in fact, directed inward, aimed at trying to understand the mysteries of how the brain computes. To give some insight into this problem, let's consider the human brain against today's supercomputer. The human brain has something like 100 billion neurons, and each of these is connected to 1,000 to 10,000 other neurons to give a total of 1,000,000 billion or 10 to the 15 synapses. And by the way, remarkably, that's about the level of complexity, at least in terms of transistor count, that a supercomputer today has. The neurons in the brain operate really slowly. They fire maybe once or twice a second. Logic gates in a computer fire at 1/3 of a nanosecond to give 3 gigahertz clock speeds today. The brain uses about 1/5 of our metabolic power, our metabolic consumption, about 20 watts. You have to increase by a factor of 1,000,000 almost, enough energy to power a small community to actually get a supercomputer to run at its computational speed, 20 petaflops of that order. And I'll describe what a petaflop means in a moment. The brain is incredibly complex. These two fellows made great progress in the 20th century on trying to understand the complexity of the brain. The guy with the wonderful mustache in the front, Golgi, invented a stain that mysteriously stained only 1 in 1,000 neurons. If you stain all the neurons, you get a black pulpy mess, useless. But if you stain 1 in 1,000, you can section the brain and see this beautiful intricacies, the wiring of brain circuits. And that's what the guy at the back in the microscope, Ramon y Cajal, studied for his lifetime, this remarkable structure of the brain. His comment, which should forewarn us, though, was that these are impenetrable jungles where many investigators have lost themselves. Well, he only knew 1/1000th of the problem because today we can stain every neuron through genetic techniques developed at Harvard and other places earlier. And if you zoom in on the mouse brain here, deep in the mouse brain in the hippocampus, there's this layer of cells that you see on the inset on the right, dense with neural bodies, and then projecting outwards are the jillions of axons and dendrites, all the wiring that projects out to other parts of the brain. Now, I teach the physics of measurement at Caltech. This is bewildering. Where do we begin? Well, let's press forward regardless because we're at Caltech and we embrace problems like this. So let's talk about brain circuits. Let's liken, using the computer analogy again, brain circuits to microprocessors. In fact, the individual logic elements in these architectures, on one hand, are neurons, and for computers are, of course, electrical logic gates. And the bit of information for the computer, of course, are these voltage transitions that go from 0 to 1, representing the elements of binary computation. And we can liken this imperfectly to the electrical spiking, the firing, or the action potentials of individual neurons. We know, for the electrical paradigm, how to approach a complex measurement problem. We put a multiplicity of electrical probes onto the microprocessor at different points, and we watch the spatiotemporal progression, the cyan traces of these voltage transitions from 0 to 1, and we can back out whether the computer is working, is the right algorithm, and so on. Remarkably, we can do the same thing with brains. We can build, using micro and nanotechnology, extremely small probes, smaller than the cross-section of an individual neuron. We can implant these gently in the brain, even over a period of a couple of weeks. The brain accommodates, the neurons and the dendrites and the axons and the capillary move aside. And then with all of these local microelectrodes, we can record a multiplicity of action potentials from a whole bunch of neurons in the brain. Now, I'd like to think about, since we're using micro and nanotechnology writ large, the same technology that we use for building computer chips, I'd like to think about upscaling this ultimately to tackling the question of entire brains. And the best way of thinking about this, of course, is thinking about Moore's law, developed in 1970 or so by Gordon Moore, which remarkably, he only had a few data points at the beginning, but remarkably, this is held true over 7 orders of magnitude of increasingly cramming more and more transistors onto computer chips. And an important juncture was crossed, delineating point in 2010 when we became routinely able to put billions, literally billions of transistors onto small computer chips. Now, of course, the consequence of all this architecture of increasing density is that we have more and more computational power, and that also follows Moore's law. I show here the slowest and the fastest of the top 500 supercomputers in the world and how their processing speed has evolved over the past 22 years. And what you see is this trend continually upward towards exascale computing. In fact, if you sum, as if they were all working in tandem on a single problem, all of the computers as of 2015 were at about half an exaflop. The unit of measure for computational power is basically the floating point operation per second. What is an exaflop good for? Well, let me just give you sort of a seat of the pants estimate. Or if you wrote the full name of every individual on the planet, 7.4 billion people, 1 million times a second, everybody's name, that's an exaflop. Well, how fast do brains compute? We know how many neurons there are. We know roughly the average activity for neurons in the brain. Where does that place us? Well, a mouse brain with about 75 million neurons is about 75 megabops, 6 gigabops for a monkey brain, and 1/10 of a terabop for the human brain. What's a bop? It's something I invented for you today. It's called a brain operation per second, in analogy with a flop. So how does this fit in with the computational speed of today's supercomputers? It's 1 to 10 million times slower. What gives? It's a mystery. We don't understand. Clearly, we need to make progress. We don't have a clue. Supercomputer, as far as I know, isn't conscious, but this slow, wet, sloppy, low-power computer, our human brains, from that emerges consciousness. So, the task at hand, can we watch all of this activity and reverse engineer what's going on in the brain? How well have we done? I show a progression of technology over 60 years since we've been able to measure individual neurons. And you see that the multiplicity of our measurements has proceeded, one might say, pathetically slowly. We're only up to about 1/2 kilobop. We can measure 500 neurons, their full-time activity simultaneously. At this rate of progress, it's going to take us 85 years to measure a lowly mouse brain. I'm an impatient guy. I'd like to do something along these lines before I retire, so we need a different path, we need a different paradigm, we need a different slope, and that's what I want to talk to you about. So our quest is the natural evolution of this line of inquiry is following Ramon y Cajal and others in his footsteps to understand the morphology of the brain. And in fact, with higher resolution, we can now look at the individual synaptic connections, this million, trillion connections in the brain, a small part of that only now. But of course, these two things are structural. They're static, they're done with dead tissue, and what we really want to do is we want to do this in living tissue. We want to see the bits flying on the superhighways of the brain. We call this the brain activity map, and I was privileged with 5 other cross-disciplinary scientists to work with Obama's White House Office of Science and Technology Policy in 2011 to help launch the BRAIN Initiative in 2013 with this idea. Richard Feynman gave a wonderful talk, a famous talk in 1959 called There's Plenty of Room at the Bottom, in which he enunciated a bunch of new fields, including nanotechnology, and he gave a very clear exposition of how you answer complex questions in biology. His answer is, you just look at the thing. Okay, well, he's a theorist, I'm an experimentalist, I am tasked with building the eyeballs to look at the thing. And in fact, it's a long history when you look at big challenges. LIGO, 40 years in gestation, leading up to September 14, evidence for collision of black holes. 20 years in development, the X-ray telescope headed by Caltech, which now gives us wonderful views of violent events in our cosmos, like exploding galaxies and black holes. And 20 years so far in the gestation of the 30-meter telescope, which will be a profound quantum leap, if you want, into adaptive optics-based telescopes. It will probably take about 10 more years before this is built. It's going to be a similar challenge to do the big science of studying the brain. Now, I want to show you what we've accomplished so far, and it looks like it's on the same line. Okay, but it's not. Just hold on for a second. Let me show you the technology first, and then I'll show you our projections of where we're going and where we want to go. We're using the technology of large-scale integration that allows us to put these billion transistors on a chip to build this new generation of nanoprobes that we can gently insert in the brain and record from a multitude of neurons. You can see some of the devices initially prototyped at Caltech over 15 years, and then a few years ago transferred in this Alliance for Nanosystems VLSI that's mentioned in the program to actually regularized foundry-based mass production. We can assemble these things into three-dimensional arrays, so we can actually look deep in tissue at a multiplicity of neurons. And in this past year, we've gotten our first data with this new generation of probes. This shows data taken here at Caltech deep in the brain of a mouse in the hippocampal region, CA1 and CA3. And you can see individual neurons spiking on individual channels. Now, I know a fair about very large-scale integration, and we have a concrete plan to go ahead in the next 4 years to upscale this to about 100,000 neurons, maybe up to 1 million neurons. But there is a problem that I don't see with the existing technology, and I know about the technology roadmaps and so on. I mean, Moore's law is actually kind of flattening out, and this is a problem for us as well. I don't think we can get above 100,000 or 1 million neurons. And I'm greedy. I would like more. So we need a different paradigm, and we've invented a new paradigm at Caltech, and it involves photons. We call it integrated neurophotonics. Now, why am I talking about photons when I'm interested in the brain? When you think about the activity of the brain, we've got spiking of neurons, electric fields. We have neuromodulators. You heard a little about neuromodulators and neurotransmitters earlier. We have spatiotemporal concentrations of these in the brain. And we have mechanical forces associated with synaptogenesis, the formation of memory. None of these are in the optical domain. So what gives? Well, what we need are local reporters. This goes under the rubric of transduction into the optical domain. Let's say we have an action potential. We'd like to convert it into, we'd like to actually read it out using photons. What we do is we put in molecular reporters, either genetically constructed, we harness the cells to make them themselves using optogenetics, or we can put in functional nanoparticle reporters. They tell us what they're sensing in their local environment, and then we can interrogate them with photons. The state of the art is quite remarkable. In the last couple of years, the ability to resolve the real-time activity of 30,000 neurons has been demonstrated. But there's a catch, a significant limitation. You got to get the photons in. And this has only been demonstrated with little organisms that are about 1/3 a millimeter in cross-section. If you apply this to the mouse brain, most of it's opaque. We can't actually get information deep. So a new paradigm is needed. The new paradigm that we invented, we're calling integrated neurophotonics, as I mentioned, and it's to plant all of the elements of an imaging system deep in the brain using this micro and nanotechnology. The elements being arrays of emitter pixels and detector pixels that emit light for interrogation and collect the photons that carry the information about the local environment of the reporters, back to our detectors. So here's a cartoon of how this actually works, with a real image taken using confocal microscopy of the cortex of a mouse. You implant this. We replaced everything on these little probes, all the nano and microelectronics with nanophotonic elements that are capable of sending out individually controlled microemitters of light and then collecting the photons that carry information back from the reporters to our single photon detectors. We've prototyped in the last couple of years, like we did for the 15 years preceding for the electrophysiological probes. We prototyped these at the Kavli Nanoscience Institute, and we're transferring it to foundry-based production now. And you can see the microscopic emitter pixels on these probes. In fact, they have microscopic light beams that are sent out into the brain. Even when you go a half a millimeter away from these probes, the width of these light beams is still comparable to the size of a neural cell body. And with that, this year we've demonstrated that we can control and interrogate individual neurons in the mouse brain. The complete paradigm, building the observatory requires from front to back molecular biologists, neuroscientists, on the back end, computational scientists, big data scientists, and so on. We label the neurons, we interrogate with light. We can do this hundreds of thousands of times, if not millions of times, in between every neural event because neurons are slow compared to photonics, and then reconstruct from all these information-encoded photons what we truly want, which is records of activity of millions of neurons. So let me summarize. With this wonderful functional imaging, we still can only go 2 millimeters deep in the brain. And this is good enough to look at transparent organisms, sort of okay for small brains, but basically a non-starter for the human brain. We've invented this new paradigm of integrated neurophotonics that we're pursuing. And our roadmap for this pursuit is, I mentioned the electrophysiology, we'll get up to 100,000 channels in about 4 years or so. But we're already engaged and about halfway through getting up to measuring 100,000 or 1 million neurons on a 3-year time scale. And in the observatory of the future, over the next decade, we hope to get to tens of millions, if not hundreds of millions of neurons. A wonderful quote to end this from Arthur Clarke, talking about our moonshot. Any sufficiently advanced technology is indistinguishable from magic. We need magic technology to understand the magic of the brain. Thanks very much.